See you, Christian?
Yeah, I think it does. Yeah, nice. Thanks.
Any other questions?
Well, Mark, thank you very much for a very enlightening presentation. And hopefully this will be a very useful adjunct to our occultation observations in the future. I'd like to go on now to our next speaker, Bob Anderson. Bob, we're a bit behind in the time, and I thank you for your patience. I'm sorry for this unexpected delay. Bob has 2 talks prepared, and I think he considers the first one to be the main one, methods for improving light curve extractions from videos. So Bob, whenever you're ready, take it away.
I gather that my microphone is working and that you're seeing my first slide.
Both conditions are true.
So I'm going to begin this talk by thanking Tony George for the many contributions that he made to this paper. As always, Tony diligently tested the new Pi movie features that have been added to improve light curve extractions. And as always, he pushed to make the new features easy to use and hopefully to be understood. So thank you, Tony. I felt I needed to start with a discussion of a couple terms that I use, particularly one, let me activate my pointer, particularly one that I use in a way that is different from the normal usage. I use the term aperture, and I think that in LiMovie and in Tangra, aperture is the thing, the little circle that circles your star and from within which the pixels are counted. But in my usage, an aperture is a square box that contains a sampling mask, and the sampling mask is usually circular, although as we will see, sometimes it has a non-circular shape. Let me see. I'm going to be talking about dynamic masks, where it's not a traditional circular mask, but it's one that is shape fit to the star. I'm using the term drop to noise ratio, where frequently we just kind of loosely talk about signal to noise ratio, since the signal we're usually talking about is the drop. Signal to noise ratio, drop to noise ratio are the same thing, but it's just a little more specific to call it drop to noise ratio. And fit metrics is going to be a critical part of this, this discussion. So to begin with, we need to ask, what do we mean by improving a light curve extraction? Well, one really reasonable answer is that we're looking for more precise timing. We'd like to have smaller edge time error bars. That's what we're looking for, edge times. We'd like to have a higher drop to noise ratio. The bigger the drop, the better our observation is likely to be. And we'd like to have a lower likelihood that the event found was due to noise. Now, I want to say that square wave occultations are the main focus of this discussion, because unlike penumbral occultations or diffraction occultations, only D and R edge times and their associated uncertainties, error bars, are needed to characterize events. Now, very quickly, the short answer to improve your light curve extractions, measure it a bunch of ways and pick the best one. I'm going to go through 3 different measurement methodologies. 2 of them have parameters, so it's quite possible to, and I commonly run 19 light curves on one star. So now you've got a fire hose, and out of that, you've got to pick the best. And that picking the best, that's the tricky part. It's got to be objective. It's got to be repeatable and based on a set of metrics that can be easily understood and calculated. And I try to show that on the next slide. So the metrics of any given light curve event solution that are likely to be useful are the edge time uncertainty. The more I've used this, and I think Tony can also echo this, the more I'm finding that this is the primary and very reliable way of choosing a light curve. Now, most of the time people would say, well, you just pick the one with the better drop to noise or signal to noise ratio, whichever term you're using. But it turns out that the edge time uncertainty is more reliable. I can't fully explain why that is. I sort of sense that it's a composite, that your edge time uncertainty will be smaller if you have a better signal to noise ratio, better drop to noise ratio. And also, if you have a bigger drop, you'll have a lower uncertainty. And so it somehow combines two really useful measurements into a single metric. I'm hand waving my way through that. Other people's experience may vary. Hopefully we'll get more experience with this in the future. The false positive metric is an indication of how very different from noise the event found is. We'd like to have a high number here, but any value greater than 0 is good. Now I'll have to explain how that metric is calculated. So I'll have to show this new term on the next slide. This is the equation, the false metric drop. The observed drop is what you saw. It was the drop of your event. And the maximum noise produced drop is what we were able to simulate as the maximum drop that could have been caused just by noise. And this little thing of subtracting by 1 means that if this number is positive, that's a good thing. That means your observed drop was greater than the maximum noise produced drop. If it's negative, the opposite is true. So we only need to look at this false positive metric and ask, is it positive or is it negative? If it's negative, that means that our event has a higher probability, some significant probability sometimes, of being produced by noise. Now, this is an almost infamous plot. It's the false positive test that has relegated many marginal observation to the no event bin. And maybe I'll just take just a second to talk about what this is. This little blue mound here is a histogram of the drop sizes that were taken from 50,000 simulations. So a single simulation is performed by generating artificial noise, including any correlation that had been observed over the length of time of the observation. So like could have been 120-second observation will generate noise, 120 seconds worth of noise. And then I ask my routine to go through and try to find, using an event duration, in this case, it was 85 readings. So start your 85 readings at the extreme left and slide it all the way over to the extreme right and find the place where you have the biggest drop and the maximum correlation, and tell me what that drop is. That's reading 1. And the histogram of all those readings is what causes this little hump. So that says the most frequent noise-induced drop was something around, maybe 45. But we had a maximum that was up around, maybe 110. But in this particular case, the observed drop was way over here on the right. This is an example of, well, the kind of observation that we'd all like to have. Just a quick roadmap of this talk. I use a case study of a Paul Maley observation, and I spent some time talking about computed dynamic masks. This talk was done a couple of years ago, but I think we need to do it again because it's one of the methodologies that is useful in extracting good light curves. And then I use a case study from an observation at heavy wind shake. And so that shows how the dynamic masks, these dynamic masks, are useful for wind shake. And then a new addition to PyMovie is a Naylor style optimum extraction. And I think Tangra calls this optimal extraction. I'm going to call it Naylor style extraction. And then I spent some time at the end talking about the caveats for each measurement methodology. Okay, so here's the case study. Many of you know Paul Maley. He'll grab his 8-inch telescope and he'll drive hours to attempt occultation recordings of dim stars, often requiring 8x or 16x integration setting on the Wattec 910. That is his camera of choice. Now, this was not one of his marginal events, but the problem was, and it's right here, you know, Paul sent me this email and he sent me this video and he said, boy, you know, I get different answers depending on what I do in PyMovie. And I'm just, frankly, I'm not happy with that. He didn't put it quite this way, but the message was pretty clear, you know, explain this or fix it, do something about it. So with the new additions that have been made to PyMovie, the first step I took was to place a set of static apertures containing fixed radius circular masks in increasing sizes. And I show this on the next slide. So these were the circular, well, they don't look very circular, but I don't bother to put circles. So I have the closest pixel arrangement to a circle for different radiuses. This is a radius 2 circular aperture. And you can see the number of included pixels goes up, and the sizes were chosen to be as round as possible and to have a significant change in the number of pixels included as we move to the bigger size. Now, this is actually a classical method. It's sometimes referred to as growth curves when you look at it in the literature. The idea is actually pretty simple. You start with a very small aperture, and it's not big enough to include all the photons from the PSF of the star. And so you're going to lose some signal. And then if you had a very large aperture, you'll get all the photons from the star, but you'll also get a lot of sky noise. So it's going to be noisy. Somewhere in between, you're going to find a golden mean where you get lots of signal from the star and not too many pixels from the sky. Okay, so the new feature in PyMovie, this is as a version 3.77. We're already at 3.8.2, so it continues to evolve. But this is a new feature. With a single click, you can add 12. You can add that set of fixed radius mask apertures and you're done. They're automatically named for you and placed. Well, I would have had to, click right here. I actually clicked right here just so I could have an easier slide to display. So after you've done that, the next step is to run PyMovie. And that'll extract the set of light curves and save them to a CSV file. So you'll have the 12 light curves at least, although you'll probably have one for the tracking star, and hopefully you set an aperture on some empty space so that you can see what a no star signal looks like. You'll open that CSV file in PyOte, and in the Square Wave Model tab, you'll set your event finding parameters. You can either mark the DNR regions if they're obvious, or what is more common is people will just set a minimum and maximum event duration in terms of reading. In step 4, you'll do a find event using the light curve with the smallest radius mask. You might as well start there and then work up. And step 5, you'll do step 4 over and over again for each of the light curves. Now, what happened is that each time you did a find event, the metrics for the solution found are automatically written to a text file. Finally, when you've gone through all of those 12 masks, you click another button and it will convert that text file to an Excel file, and you can name that whatever is convenient at the time. And in step 7, you're going to examine that Excel file, and you're going to do that hard part. You're going to choose the best light curve to use for a report. So here is an example of that. This is what happened when I ran all of these are automatically named. So it is the signal. In other words, it's background subtracted. It was a static and it was a nest 1, and you can do 2 nests if you wanted to. I've never needed to, but you could. And it runs from a 2.0 radius to, in steps, all the way to an 8.8. The smallest time uncertainty is right here. And you can see it was a little higher at the 2.2, it dropped down, and then it smoothly increases, suggesting very strongly that this is a good candidate. We see that the drop to noise ratio is 1.37. That actually turns out to be the highest in this column. That's a good thing. And when we look over here to that false positive metric, we see we have a number that is not only positive, but it's much greater than 0. Just very quickly, I'll show that slide again. What that means is that for this observation, the observed drop had this relationship to the maximum noise-induced drop. So going back to where we were, I should say that Occult stated that the mag drop for this event was 0.5. So the mag drop is reasonable. The mag drop is not the biggest number. That number seems to sort of grow, even though the drop to noise ratio is getting worse. So what's happening is it's just getting noisier. You're getting a bigger drop, but the noise is beating you. It's growing faster than this drop. So this is the best. This is the one that you would pick for your report. One of the things I should say is that edge time metric comes from a simulation. So that means that if you run it again, you're going to get a slightly different number. It comes from this 50,000 simulation run. So it's a natural question to ask. The false positive metric and the time error are both going to have this jitter, if you will. If you run 50,000 more, you're going to get a slightly different number. So I just did a small study in which I ran the same thing 4 times, and I recorded the false positive metrics and the time error. And you can see that they are a little different run to run. This is an insignificant difference here. Remember, anything greater than 0 is good. And here we see that the time error uncertainty is quite reliable, has a very small standard deviation and a very good mean. And the same was true. I just ran a couple of other of the mask sizes just to make sure there wasn't anything odd. So I'm concluding that the edge time metric is typically good to about 2.5 digits. So it is repeatable and it's accurate. Now, we're not done with Paul Maley's. This was Circe that he did. So far, we've just used the classic aperture photometry method of summing the pixel values enclosed in a circular mask, subtracting the sky background value to get the star signal value. But there are other measurement methods available. So I'm going to digress to another case study to introduce this other method. We'll come back to Maley, and we'll add more light curves that employ this additional measurement method. We need a little history. The motivation behind the original development of PyMovie was to create a tool for dealing with videos that had been recorded in windy conditions. You can blame Tony George for that. He and I were talking, and he said, I got a problem, and maybe you can help with this, and the rest was history. The issue is that wind-shake videos distort and smear the star image to such an extent that putting a fixed size circular mask in order to encompass all of the pixels comprising the star image throughout the whole recording session, often has to be so large that you get a lot of extra sky pixels, so you get an overly noisy light curve. So the core idea in that original PiMovie version, I think it was like 0.7 was the original release, was to shape a mask that closely followed the contours of the star image, thus minimizing the number of extra sky pixels and giving a lower noise light curve as a result. That had barely been operational when there was an occultation by Pluto that was recorded in gusty wind conditions. And that is the next case study. So I'm going to start with a little video that graphically shows the problem. Let me see, I have to turn this into a video. I think can I click on that? Nope, I got to get my laser pointer off. Okay, so I've started the video and you can see wind shake. Doesn't look terrible. Oh, what was that? That's what happens when you have some significant wind shake. Okay, enough of the movie. Let's go on to an example of, it's not going to stop. Oh, it likes to go again. Okay. All right. I've chosen one of the frames that showed the one of the smears, if you will. Here is the image being smeared, and this is the shape-fitting mask that PiMovie fitted around that smear. And this is what a circular mask would have looked like to have encompassed reliably all of those pixels. Now that's sort of an outrageous example, but it was not rare in this video. Just a quick little show and tell of how that dynamic mask or shape-fitting mask is calculated. We start with a star image. It has a PSF shown sort of crudely by this 3D drawing. And in the first step, I smudge it. I run a 5x5 Gaussian filter. What this does is it smooths it and it kind of smears the edges out. So that gives like a little boundary. And then on the next step, this is the smudged target star. I run a cut line. It's what I call threshold. So this had a threshold of something. This looks like, maybe it was, 20, 27 or 28. And so every pixel that is below that cut line is set to 0. That means we don't want to measure it. And everything that is above that, we want to set to 1. And so the mask then is the one that we saw in the previous slide. And here was the benefit. This was a light curve. It was an occultation of Pluto. And of course, the reason that we're getting these gradual declines is that Pluto had an atmosphere, and an atmosphere such that in the center of the occultation, due to refraction, this is not diffraction in this case, it's a simple refraction caused by Pluto's atmosphere. So it was expected that there would be a central peak, and we can see it. This was what a light curve would look like that used a circular mask large enough to mitigate wind shake. And it's mitigated because we don't have big excursions. But this is what we got by extracting using that dynamic shape-fitting mask. And the researchers that shared and challenged the newly developed PiMovie with this video were quite happy with this result. It's roughly about a 2-to-1 improvement in the signal to noise ratio as you run along here. So that was PyMovie version 0.7.0. Okay, now I want to indicate as well that these dynamic masks can be useful for other reasons. I call these speckled images. This is an example that Kirk Bender loaned me. He got this on a big telescope, a 36-inch telescope. And let me see if I can run a movie. This is what a big telescope will let you see whenever you have some high altitude turbulence. It causes your image to break up, and it looks a lot like wind shake, but it's not. It's the image being fractured and shattered. Okay, so some caveats about this dynamic mask usage. In order to compute a form-fitting dynamic mask, the star has to be bright enough that there are at least 9 pixels in the resulting computed mask. If it contains less than 9 pixels, PyMovie reverts to a fixed circular mask. It's a size that the user will select. Usually you select a very small one, radius of 2 or 2.4. But you have to be concerned that that shift from a computed mask to a fixed mask can introduce a glitch, a dip, or a spike. But if you're careful, that mode shift will be benign, but you do have to be careful about this. Now, PyMovie helps with this by providing a color-coded plot, which looks like this. So this is an example. All the red dots were measurements that were taken with a successfully computed dynamic mask. Where you see the black triangle, what happened was there wasn't enough light, if you will, from the star to be able to compute a mask that contained enough pixels. And so PyMovie said, we're going to use your default mask. Now, down here, I'm showing the number of pixels that were in whatever mask was being used. So you see they're fluctuating. That's the dynamic part of the mask formation. But even where these black triangles show, you don't really see, because this triangle corresponds to about here. So the number of pixels that were included in the substitute mask was very similar to those that were in the dynamic masks. And that is true. This happens to be where the event occurred. Interestingly enough, the event also shows up down here because suddenly the average number of pixels in the mask has dropped. Well, that's because the light has dropped. It's kind of fun. It's not as effective as just doing a search for an event on the light curve, but it is possible if you wanted to find your event edges by telling Pyote, use the number of pixels in the mask data set. I don't recommend it. So I want to return to what we were doing with the Mealy study. And new again to PyMovie is a single-click way of adding 6 dynamic mask apertures all at once. So you would simply position right here, you'd do a right click, and then you'd do a left click, and you'd get 6 dynamic mask apertures. Now, I already have 12, so that means I'm now up to 18 apertures. This will be a little familiar. You've got to run PyMovie, you got to open it in Pyote, you got to set your event finding parameters, you do a find event for each one in, now you're looking at the ones from the dynamic mask, and you repeat that for all 6 of those, and you save those to the Excel format, and then you open the Excel format and you pick the best. And this is the Excel spreadsheet that we got. Now, this had been the winner back when we only had static circular masks. This was the best. But if we look down here, we see that the dynamic mask at a threshold of 16 counts is lower than the time uncertainty from the static mask with a 2.4 radius. And here we see an example where the DNR was greater here than it was here. But you notice the time uncertainty was larger up here than it was down here. Since timing accuracy is what we're looking for, that would be our preference. And if we look over here, our other big metric was, how different is it from something that could be produced by noise? Anything greater than 0 is fine. And this is well away from being a source of noise. So that means that there is a new best. Now, so we've now used 2 of them. We've done the classic aperture photometry method, and we've done the dynamic form-fitting mask. But there are other methods, and in particular, I'm going to talk about one that comes from a paper by Naylor. And let's see if I can move on to that. This is the paper. It was Tim Naylor. This was published back in 1998. And this is the abstract that he published. So he said it's whether optimal extraction techniques that were used in CCD spectroscopy can be applied for imaging photometry. The issue he was dealing with is CCD spectroscopy was one-dimensional, and he wanted to explore whether it could be used in 2 dimensions. And what he found is that if he takes this method from the CCD spectroscopy and apply it to the 2D case, that he can get about a 10% gain in signal-to-noise ratio over normal aperture photometry. I didn't want to burden this portion of my talk with a lot of arcane equations, so I'm going to hand wave my way through what this paper says and how PyMovie uses one of the findings of his paper. If you want the math, the paper is easily found, and it's not a very difficult read. I want to emphasize again, he only promises a gain of around 10% in the signal-to-noise ratio. It's not a lot, but it's still worthwhile in some cases. So on to the hand waving. Okay, so the idea underlying what I'm going to call Naylor extraction, and I use NRE for that's my terminology. And the principal idea is that brighter pixels have a higher signal-to-noise ratio. So to use this idea, what you want to do is to calculate a set of weights that are used to increase the influence of the bright pixels in a star image and decrease the influence of dimmer pixels in summing the star image pixels. Now, in standard aperture photometry, the weights are set to 1 for all the pixels that are being included in the sum and 0 for all others. But in Naylor, you've got within the sampling mask, your weights run from 0 to 1. And there's some normalization that has to be done, but in effect, that distinguishes it quite clearly from the standard aperture photometry. Okay, so I found this out that any set of weights that are bigger for brighter pixels and smaller for dimmer pixels will help. I tried a number. Anything works as long as you say, as long as your weights are bigger for brighter and smaller for the pixels. But the question that is answered in the paper is there an optimal set of weights? And that's why he titled his paper as he did. So to develop a set of optimum weights, the scheme is to get a PSF of the star image, and you make the assumption, it's an assumption now, that it's a 2-dimensional Gaussian. So it could be longer in the X direction or in the Y direction, or it could be, slanted at an angle. Now, the point is that you will then have an equation which involves a peak value, I max, and it has an X width parameter and a Y width parameter, and it's written as a function of R, which is the distance from the point where the function has its peak value. Okay. The next observation is that given a pixel value and its corresponding distance from the center, you can calculate an I max. You've got everything you need. You've got an analytic expression. Now it's nonlinear, but it's just a matter of some numerics to take the pixel value and the distance from the center and calculate an I max. So now you have an I max calculated from a whole bunch of pixels. So what do you do with that? So now you've got n pixel values from your n locations. N is the number of pixels in your mask. And so you can calculate an array of these I max values. I'm showing as a subscripted array now. And the question is how you best combine these estimates. Well, statistically, the way you combine n I max estimates is to get a single value is that you divide each one by its variance, which penalizes the dim ones. You sum the result and apply a normalizing factor as required. This is basically a weighted least squares estimate where the weights are inversely proportional to the variance of each estimate. Okay, so this all could have been summed up with a whole bunch of really arcane equations, but I hope that the hand waving is a little easier to get to. Now, Naylor gives two formulations for calculating these optimal weights using the above method. Okay. Now, I use the one that Naylor refers to as sky limit. And what that means is you have such a dim star that the sky almost wipes out the star. And the point is now that the pixel variances can be assumed equal. You don't have to do anything special for the pixels as a part of the star. And that simplifies the equation, and they do not need to be calculated as you go forward. And that has one of the advantages is that you get a really simple form for the optimum weights. They're simply proportional to the magnitude of the 2D Gaussian PSF profile. And this sky limited formulation also means that it's particularly good for dim stars, and it can be applied to occultations that go clear to zero. Okay. Returning to our case study. New with PyMovie is this new menu item, which is add an NRE aperture. When you click this, it will automatically add and name and set all the necessary parameters so that when PyMovie does its extraction, it will automatically go through. It will figure out what the PSF is of that target star. So that's an instrumental PSF. It fits a 2D Gaussian to it and calculates the weights. And that was done. And we went through the usual process. We went to PyOte, and we asked it to take the data for the star that had the PSF associated with it and do your calculation. And we find it's got a pretty good time error, 0.8. Remember, our best from the static nesks was 0.787. If you'd only have these two methods, you would have chose this one, but this was a pretty good one. And that's been a pretty reliable experience that this Naylor extraction is generally a good answer. Sometimes it's the best, but it's not always the best. You really need to look at the other methods as well. And as you recall, our winner was down here with the shape-fitting dynamic mask. Now, this is what the fit looked like for the one that was best. So I threw up and chose right here, I chose to display the light curve for the extraction that was deemed best from our study of the Excel spreadsheet. Now, this is bonus slide. It's sometimes said that one might get a lower noise light curve from the raw aperture sum because there's no background subtraction. Therefore, there's no additional noise from that calculation and operation. Now, I can't recall any example where that approach helped. So I examined the aperture sum metrics in this case, just to make sure that a better solution wasn't being missed. And it's really an eye chart, but the noise that you're looking for is right here. So this is the noise in the baseline. And if we look here and we compare it with the static mask, well, it's not much different. And if you just eyeball this and you eyeball up here, you'll see there's essentially no difference in the noise. And it actually had problems with, you ended up with some negative false positive margins. So that's the bonus. So I want to summarize the caveats that I've covered in the methods. I have none for static masks. I believe that they're always applicable. Sometimes you have to make them really big, but they're still applicable. The dynamic computed masks work best with a star image that continuously allows a mask to be formed. So that's good for, like you had a bright star and a low mag drop operation. It's going to be really good for that. Sometimes a mask can't be formed, so you got to be careful about that transition to a default circular mask, but that is something that can be dealt with. The Naylor style noise reduction requires a well-defined and stable PSF star image. So it will, I guarantee you, it will misbehave when applied to a windshake video or a speckled video or a defocused video, which occasionally people have to do when the star that they're observing is very, 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 very bright. Defocusing is one of the techniques that people use rather than change gain or change their exposure time. I also want to say that most of the occultation observers have chosen their camera optics so that the star image is undersampled. That means you don't really have a good sampling of what the PSF is. So that means that the Naylor style extraction is already a bit crippled because it's based on a PSF, and you're deliberately undersampling, which is good for the occultation observations so that you concentrate most of the star photons in just a few pixels. But the Naylor type functions a little better with an oversampled star image. So while it is often a competitive solution, it is frequently not the best. Now, in conclusion, I want to say the method caveats are worth keeping in mind, but usually the fit metrics will show you when it's not working. So you can run them all. Don't have to think about it in advance, but it does mean you'll have a few extra lines that you're probably going to throw away from the Excel file. The most reliable metric is this one. It's the edge time uncertainty. It's repeatable with more than 2 digits of precision. The supporting metric correlates pretty closely with edge time uncertainty. So it's not really an independent metric. It's somehow kind of locked up in this, and this. Yeah, they tend to track. And finally, the indicator that this is not noise is that false positive metric, which has the characteristic that small differences are unimportant. So this metric is not one that is normally useful for deciding between two extractions. And thank you. Are there questions?
Yeah, Bob, this is Vince. You mentioned a cut line. Is that something you arbitrarily selected, or is that something that's done dynamically?
That's done dynamically. Let me just stop my share here. That's done. That's done when you select it's one of the parameters that you have to give to PyMovie. You'll say, informing this mask, use this cut level, as I call it, threshold. It's the number of counts above the baseline, if you will, the baseline of the PSF of the star. So that's usually set at 1/2 of the standard deviation of the pixel noise. It turns out to be a pretty good way to set it. So for most of the observations, you're going to find that that's the initial number is going to be something like 4. And when you click on PyMovie and you ask to put 6, it says, where do you want me to start? And you'll tell it 4. And then it'll say, so, and for the next 5, what is the step? And usually I'll use 2. And so that'll give you a set of dynamic masks, nest of dynamic masks that have the cut threshold set at 4, 6, 8, 10, 12. Does that answer your question?
Yes, thanks.
This is Steve Preston. I had a quick question on the false positive test.
Yes.
Since that's based on the estimate of the noise distribution, to what extent do we have an idea of how accurately we've measured the noise distribution? Or is there, interesting question, there's not a lot of samples for the noise distribution in some cases, and how do we know if we have enough to feel confident in the false positive test that's derived out of that? Maybe some ability to tweak the noise distribution, see what happens if we're off on that. The noise distribution is taken from your observation.
I want to say something.
Who wants to say something?
Sorry, I was speaking to my wife. I'm just waiting.
Oh, you are. Well, I see your hands up there. Okay, so let me, Steve, the way that test is run is the observation that presumably you didn't get an event out of. You select points, usually all of them, and you say, please extract the noise statistics from my observation. Now, if you happen to have an area that needed to be excluded, like there was something that sort of looked like an observation, there was a dip, and I really don't want that included in my statistics, there is a way of saying, use these points, but avoid these and use these. And so from your observation, your actual observation data, we extract the noise statistics, including the correlations that are almost always present in the data, and have that may be one of the reasons why that edge uncertainty metric is has the reliability that it appears to have, because it does include the noise correlation, which you otherwise might not see. Does that help, Steve?
Yes, I guess the question is kind of how do we avoid the trap of someone accidentally not including enough points when they're determining how much of their light curve is being used for that. If they really winnow it down to just a few points either side of the event, either because they have an issue with the recording or they're just careless in designating what part of the light curve to be used.
Well, I don't have any way of protecting against fraud. what that would be.
Well, it wouldn't have to be intentional fraud. Obviously, it's just a question of, it would be interesting to have a measure of the uncertainty and the accuracy of the noise estimate.
Let me see. I'm not sure. I think that in the log file, it does indicate the points that were selected for the noise. And so somebody could examine the Pyote log file and determine how the user selected his points for the detectability analysis, the false positive test?
Couldn't it in theory be
That's-
possible to
that's
come up with
correct.
some sort of a rough estimate of the, you know, the accuracy of the noise distribution measurement, measurement?
No,
And in theory, you could run a-
there's really no way to get that because you only have one measurement. You only have one observation.
Well, I mean, you have, but you know what I'm saying, though, you've got a sample of 100 data points is different from a sample of 10 in terms of the accuracy of your estimate of the
Oh,
of the
well,
distribution.
typically you have 1,000 or more. I mean, people do.
Yes, but I'm just saying it'd be nice to have a check just to make sure it doesn't go too low. I agree that most of the time it's not an issue. It's just an interesting question whether it'd be possible to add a check to say, oh, looks like you didn't include many points in the noise distribution.
Well, then you'd have to,
Yes,
then you'd have to ask them to present that data. I can't imagine that comes up very much. Usually,
no, I wouldn't think it would. But it's just something to keep in mind as we, we rely on that false positive test. That it also relies on the quality of the noise distribution presented to it. So anyway, thanks.
Can I come in here because I've got a light curve I'd like to display and ask Bob for your comments on. First of all, can I congratulate you on putting in an optical extraction process in Peyote? It's a useful thing. It certainly doesn't improve things all the time, but it's a useful thing to have.
it's in PyMovie, Dave, not Peyote.
Oh, yeah, wherever it is. Here's a light curve it's looking at. There's the target star. That's a comparison star. Now you can see that the light film for the target has got variations which are not in the reference star there. This is the putative event, and you can see you can imagine there's an event there, but you can also see you can draw a line through there. And it's similar to, you could draw a line through there. And those types of characteristics not in there. In terms of the way you develop your false positive test and your noise things, how do you deal with these, what I would call long-term, low-frequency noise variations in assessing your noise possibilities?
Two ways. First, the user would have to select those regions where those dips aren't occurring. So you've got two pretty good size stretches where things look like they're behaving pretty well. The second is I take the first derivative of that and calculate the statistics and then adjust them by the square root of 2 to get back to the original. What that does is that takes out any linear change so that if everything was on a slope, for example, you would get the same answer. So I suppress any linear and I allow the user to select the areas to sample his noise distributions from.
But the concern that I have with that is the extent to which that is those determinations, which for this event, you're looking at, I think that an event was due here. I mean, that's a 5-second intervals per step. To what extent does that type of approach come down to there being the influence by, for other reasons, I think there's an event here, and being selective about where you choose your noise, you get a bias.
Dave, can I ask you, what did the false positive test show on this light curve?
That my understanding from recollection, it said it wasn't a false positive.
Okay.
And I mean, here you've got a noisy thing. that's for a range of other events. You could say that there was a nice, clean occultation event. You don't have drops like that. I mean, there's issues. I have seen curves like this where you look at something like that and you say, is it actually an event or is it a long-term noise variation? And it's interesting that this comparison star doesn't have that variation. So whether that's a measurement aperture technique, I should
don't-
say this was a magnitude drop of 0.1. And you can see over here the background sky brightness was quite bright.
So I would chime in here. Couple of things. So since the comparison star is so flat and there's no variation, and the target star has a lot more variation in the whole light curve, it's an indication that you could probably choose a better aperture.
Yep.
Or you could choose a better analysis methodology in PyMovie. So I see you're using a Tangra, and you could try different methods in Tangra too. But what Bob is doing is it would allow you to try the other methods and see if they will improve the overall light curve. The other
And
thing,
that's
I
what we
was
do
going to say,
routinely.
Dave, I think you're barking up the wrong tree. You started by talking about the false positive test. False positive test is not one that is used to include an event. It's used to exclude one.
okay, and then I wanted to
But I
So,
see
Dave,
people's
hang on, Dave.
claims.
hang on, Dave. So you pointed to a wedge of dots over there just to the right of the main dip. And you say, well, how could I be sure that wasn't the true occultation? So you can clip that out, start left of that down area, and mark all the points to the right, and then run another analysis. And ROT will test that one dip against all the other noise in the right side of that light curve to see if it would pass a false positive test. If it doesn't, then it's just a noise dip.
Yep.
If it does pass, then you have more questions. But I still think that in this case, you need to try different apertures and or different try PyMovie and see if some of the other methods don't work better.
At this point, Roger probably should be stepping in, but I'm going to step in. And
I do want to step in, but you go ahead, Bob.
well, the step in was this kind of a conversation goes around in circles, and I don't think that it's necessarily that beneficial. I'd like to move on. We're already an hour past, and poor Kai is waiting to give his weather report there at the end. So,
Okay, so just before you move on, I'd like to make one more comment in general about the evaluation of the fit metrics. So recently I had a light curve where I ran the nested static apertures, static masks, and the very small masks actually had the very best timing error, the very lowest error bars. However, because the mask was so small that it wasn't sampling all the star, when I looked over at the false positive metric, it failed the false positive test. So the little teeny, very narrow but very deep mag drop event that I found with the smallest aperture mask wouldn't have been separable from noise. Whereas when I looked at the larger masks, which sampled more of the star light, I then found a good light curve that passed the false positive test. So that single metric, the timing error, isn't necessarily always the best. You got to look at the DNR, and you got to look at the false positive metric to come up to a final conclusion.
yeah, those are the three I always look at.
Yeah, thank you.
would just like to point out that the studies that Naylor, what's his name, Naylor did was all with high signal to noise ratio stuff and with a broad enough star image to justify his Gaussian applications. And the problem that we have is that we deal with very low signal to noise ratios, and we deal with very tiny star images where I deliberately try to use f2, where even the first diffraction ring is on the same pixel as the central image. And so the point is that the application of point spread function measurements has never been proven to be valid with the type of images that we are using.
Yeah.
I'm sorry, but I believe that strongly. It has never been shown to be valid with these images. They're completely different from the stuff in the literature. In fact, you can find an article where the lowest signal to noise ratio they ever had in their study was 3.0. Well, let me tell you, over half my light curves have signal to noise ratios lower than 3.0. And as I say, it's not even, that kind of thing isn't even included in their studies.
Yeah.
And so for this reason, I distrust optimal extraction. And I think, if anything, the study that you've just demonstrated, Bob, it supports the notion that optimal extraction is not trustworthy. That's what I have to say. And that's just the beginning of my comments. I better stop.
I see.
Let
Well,
me just come in very briefly. This whole issue, as I mentioned yesterday, we had a situation with prediction side where everybody was saying, my prediction is right, and everyone was wrong. We have a situation, and it applies to every light curve interpretation technique. We have a situation where we look at the light curves and we do these theoretical studies using whatever techniques to draw conclusions. And on the face of it, they look quite good. I mean, I have no reason to criticize per se, Bob, what you're doing in Pi Movie Peyote. My underlying point in all of this with these noisy signals is, as best of my knowledge, we have never, ever done field testing to ensure that in reality, what we're interpreting from these light curves actually matches what's going on. We're operating this at a totally theoretical level. And yeah, I'll leave it at that.
Okay.
Well, those are good points, David, and I appreciate your raising them. As Bob suggested, we do need to go on.